Okay, so I'm going to talk about Spack and the US Exascale Computing Project. ECP is pretty big in the US right now. And I think people wonder what this is. Is it good? Okay. I don't know. Oh, that's good. That's great. Cool. Awesome. Okay, so ECP has a rather long definition, but essentially it's a large, something like 300 million a year project in the US. It's a collaboration of 17 national laboratories. And the goal is actually not to deploy exascale machines. So it is to prepare an exascale-ready, exascale-capable software stack. So the procurement of the actual exascale machines in the US is up to the facilities, and that's something that's going on concurrently. But ECP is really a software project. And because of that, Spack has started to play a pretty large role. So if you look at ECP in the large, it's 7 years, it's 1.7 billion over 7 years, so something like 300 million a year, and I think it ramps down. There's 6 core labs and 17 total labs. 3 focus areas, so there's an application development thrust where the app people are. There's a software technology thrust, and there's hardware and integration. And the way this is supposed to work is that the applications are sort of is a point of the whole thing. We want to have applications ready for exascale. The software technology, I mean, applications are software too, but software is sort of the infrastructure and the support libraries and the numerical libraries that support the applications. So this is supposed to build a software stack that not only these apps can build on top of, but also labs and industry in the future. And then hardware and integration is something that came sort of in the second year of ECP. It's a new piece of the project, and it's specifically responsible for integrating the software stack that we're producing with the facilities. And so that's an interesting aspect because it wasn't there originally. It was sort of, and the facilities said, hey, there's no funding for us to integrate all this software that you're producing. We need to have some interaction. And so they introduced the hardware thrust for this reason. So there's actually dedicated people at the different facilities who are supposed to interact with ECP and make sure that the software gets deployed. And overall, it's like 1,000 researchers and 100 R&D teams across all the different labs. So it's a pretty interesting project. There's a lot of different science applications in ECP. I won't go into the details of all of these, but it spans a whole wide range of things. So there's compressible flow, higher order hydro, climate, urban systems, subsurface, nuclear reactors, there's wind, and then there's also other projects with the NNSA labs for national security applications that are sort of included in the project. This is the roadmap for exascale in the US. You can see that we are here, where the #1 machine right now is Summit at Oak Ridge, and Sierra's #2 at Livermore. These are both Power 9 GPU machines. And if things go according to plan, I guess Perlmutter is being deployed pretty soon here at NERSC. Crossroads is yet to be announced. Aurora at Argonne is supposed to be the first exascale machine. We'll see how that goes. And then Frontier at Oak Ridge, I think people are this just got announced. This is a large AMD GPU machine that's going to be deployed there. And then in 2023, Livermore is yet to announce their machine, but this should be happening pretty soon. There's going to be the El Capitan machine, which is another, it's in the same procurement as these 3. And so that's the last one to be announced. I don't think I need to go into the specs of these machines for this audience, but at the heart of ECP software is a whole lot of open source software. So these are the different, this is a sampling of projects from DOE. So the software technology stack covers things from OpenMPI and MPitch, so familiar technologies, to newer performance portability layers like Cocos and Raja. So these are C++ libraries that help you run across GPUs and multi-core machines in a portable way. UPC and GasNet are both in there. There's file system projects, so Adios, ZFS, Lustre, those are different open source projects. And then there are meshing technologies in the ECP. Some of these are not actually in ECP. These are just major open source projects within DOE. But MFEM definitely is, Chombo, Amrex. There's Viz projects, resource managers, and then there's parallel solvers. And I think one of the newer things that started emerging within ECP because of the way that the software landscape is changing is that there's a lot of packaging and build technology actually in ECP. So there's Spack, which I'm going to talk about. There are container technologies like Shifter, Singularity, and Charlie Cloud, and there's actually a dedicated containers project under ECP now. A lot of people are really starting to think about how they would deploy this really complex software stack in a way that people could actually use it. So there are a lot of challenges to that. There's a lot of software complexity. I'll talk a little more about that in just a second. There's lots of languages, there's lots of low-level libraries. All of these things have to be integrated across diverse architectures, and we don't know what all the architectures are going to be yet, so that makes it even more fun. And then there are security requirements. So when interacting with the facilities, a lot of the time, the obstacles to really running a build pipeline or deploying software are organizational or security-based. They're not necessarily technical problems in the sense that they're related to building the software. They're actually related to building infrastructure to deploy the software. So to give you an idea of how software complexity in HPC is growing, consider some relatively simple packages like Nalu. This is an unstructured low Mach flow code that uses Trilinos as a solver. I think that's where most of the dependencies in this graph actually come from, is from Trilinos. This is a Sandia code. That's one thing. Consider Deal 2, also part of some of our software packages, also uses Trilinos, but a lot of other solvers underneath. It's even more complex. And then you even get into some of these data packages like R, where this is R. These are all the R packages over here, and this is all the stuff that you have to build under R to run all the R packages, so all the native libraries. This is tremendously complex. And even for proprietary codes. So this is a production multiphysics code at Livermore. It's called Aries. It's used for inertial confinement fusion and other applications. Half of this graph is open source. Actually more than half of this graph is open source. The blue stuff is proper open source software from outside of Livermore. The red, green, and yellow stuff is Livermore software, some of which is open source. And all of this has to be put together in an application. So this team actually builds 36 different combinations or 36 different configurations of all of this nightly across several different architectures. And so integrating this stuff is getting much more complicated. If you consider ECP as a whole, and I think people have seen this before, there's 15 plus applications. I think there's actually 25 in the latest iteration of ECP, 80 or 90 software packages. There are 5 target architectures that we have to care about. I guess you can cross Xeon Phi off the list there, because it's not around anymore. But there may be new architectures that we have to care about. Maybe 7-ish compilers, 10 programming models if you include all of the different things people are programming in, and 2 or 3 versions of each package because some things are incompatible with other things and you have to build with special versions. So if you consider the number of installations or the number of combinations that you could build with all that, it's like 1.2 million things or maybe more. That's not scalable. It's not sustainable for people to do by hand. And so we really want to be able to reuse this software in a scalable way. So I think with all of these things coming together and the labs being in, I guess, a common project for the first time where one of the main focuses is really software engineering. I think in some sense ECP is less of a research project than prior efforts in DOE in that it's really focused on deploying the software stack. People realize that they need something to manage the complexity. So Spack has started to catch on within ECP. It's not necessary. I think Spack got traction within ECP not just because of ECP, but also because it's getting traction around the world. So Kenneth has a graph like this for EasyBuild that you're probably familiar with, but this is all the places that Spack is used. We get over 2,000 monthly users on the doc site every month now, which is pretty cool. And it has over 3,100 packages, and contributions have been growing over time. Spack it's an automated build tool. It wraps your package installation system and drives basically the installation of these large software stacks. And the target audiences for Spack are pretty diverse. So we're targeting not just HPC admins, but we're targeting users, so just people who want to just run software either on a laptop or on a cluster or on a really big machine. We're targeting developers who are actively developing applications, and we're also targeting HPC facilities who have to deploy these massive stacks of combinatorial software explosions. And so it started to be used at many top HPC centers, so DOE sites, other sites abroad, and it's actually reduced the deploy time quite a bit. So Oak Ridge, before they started using Spack, it would take them about 2 weeks to deploy all of their 1,300 software packages as they build. They can build that overnight now. It's gotten traction outside of HPC in kind of interesting ways. So Spack is actually used within the high energy physics community. So, and it's in OpenHPC, which is pretty cool. Oh, is that a question?
Yeah,
Sorry.
No,
yes.
I was just wondering in your Oak Ridge example, I mean, the build time doesn't go down. What led to the drastic reduction in
It's that they were doing it, so their previous system didn't actually manage dependencies, right? And so they would have to actually manually install each piece of software and manually configure it. And so, I mean, that's really just human time that you're removing from the equation, right? And it's the ability to quickly specify new configurations when you put the machine on the floor. So I'll talk about this in a minute, but I mean, like the Aries team that I showed, they had a similar reduction in deployment time. So it used to take them like 2 weeks to deploy on a new architecture with all of their dependencies, right? And a lot of that is really just tweaking configurations for all the different software that's in Aries. And so now that they're able to do that rapidly, they can get running in a few hours on a new machine instead of weeks, which is pretty cool. Spack is designed to be quick to install. So all you have to do is clone it from GitHub, and then you can start installing things. You don't have to go through a lengthy installation process. And it's designed to be flexible. And so what does that mean? I gave a tutorial on this, I guess, 2 years ago, but I just wanted to sort of emphasize the different features before I get into the details of how it's being used in ECP. It has a syntax for installing things. And so at a basic level, it's kind of like a package manager that you would expect. So you can say Spack install, say MPI leaks. It's a tool that we develop at Livermore. That's unconstrained. It says, give me MPI leaks. I don't care how it's built, just get it installed. And so Spack is able to pick defaults for all the things that you didn't specify. You can be specific. So you can say, give me MPI leaks at version 3, and you just write that on the command line. You can ask for a particular compiler and a particular version for the package dynamically. So you can say, install this thing with that compiler and that version. And let's see. You can ask for build options dynamically. You can say, no, I want the version with threads. And you can inject flags into the build directly from the command line. So if you want this thing built with specific compiler flags across C and C++, you can put that in there. You can say, build it with these flags. And you can build multiple versions with different types of flags, and those are considered separate. You can target, you can do cross-compilation on things like the Cray machines. And then the other thing about Spack that I think is kind of unique is that this syntax applies to the dependencies too. So if you want to do something specific for your dependencies, you can actually say, I want MPI leaks built. I know it depends on MPI. I want to install it with mpitch instead of OpenMPI. And I want mpitch at this version with this compiler. And so the syntax is recursive. You don't have to know what the DAG structure looks like for the most part. And you can be specific about how you want the different dependencies built. So you can very quickly install different configurations of things. From a user point of view, it's pretty simple. You just say Spack list, and you can see what's available in Spack. It'll print it out like this. It has over 3,200 built-in packages. And what you may notice here is that these are just names. So every one of these is a name for a package. It's saying I'm going to install ndiff or ncurses. It's telling you what you can install. But you can actually, each of these is really templated. And so it's a template for a build. And you can install it in lots of different ways. So if you ask Spack what's really installed, you say Spack find, and then it actually shows you the specific instantiation of those templates that are installed. And so this is saying that for Linux, RHEL x86-64 with GCC at 447, I have all these packages. With GCC 482, I have all these packages. And Intel 1402, I have all these packages. And this is one view of the data. We're really storing the full DAG of all this software in a database. So we know what's installed, what all the dependencies are built with. You can mix compilers. This is sort of a high-level view. The way that we install stuff in Spack is designed so that you don't have to think about how you built the software when you run it. So everything here is installed in its own prefix, and it's RPath to all of its dependencies. So it basically knows where to find all the dependencies. You could run a Spack binary right out of the directory that it's installed in. You don't have to load a module to do that. And it has some pretty advanced query capabilities. So if you want to know, things about specific packages in Spack, you can say Spack find call path. It shows you just that package, how it's installed. And it can give you the full dependency information for everything that's installed. Things in Spack have hashes. And this hash is a function of everything that it's configured with, including all of its dependencies. And so you can look at this data and you can see things like, oh, I see that I can't build against this version of call path because it's built with the wrong boost version. This one over here has the boost version that I'm compatible with, and something is exploding because I may be incompatible. So we store all that metadata. And the packages are pretty simple. So this is an example of a Spack package for cryptkey. which is a SN transport mini app from Livermore. It's got some metadata up here. CryptKey is just a Python class. It extends the CMake package, which basically just says I'm following the typical CMake build pattern, so use build support for CMake. And then you can say, this is where you download it. These are the different versions that are available and their checksums so that we can verify the download. And then this is maybe different for people who are used to easy build. Spack has variants. So for any particular package, you can have multiple versions of it. You can say, here's an option that I want to be enabled or disabled, and users can request it on demand. And you can have dependencies that are potentially optional. So in here, you say variant MPI. That says whether I'm going to build CryptKey with MPI or whether I'm going to build a sequential version. So you can say CryptKey plus MPI or CryptKey minus MPI. OpenMP is the same sort of thing, either with or without OpenMP. And then Spack only depends on MPI when MPI is enabled, right? When the MPI variant is enabled. And so this basically says that I can build many, many versions of CryptKey with this package. The other thing in Spack is that the versions aren't fixed. And so you can say I depend on CMake 3 or higher. That's all I need to build CryptKey. And I can say that this is a build dependency so that it's only useful at build time. I only need CMake to build. I don't need to link against it at runtime. The package build instructions themselves are templated. So in here, you can actually refer to the variants. So you can say enable OpenMP, that's a CMake argument, when the OpenMP variant is in my spec. And enable MPI when the MPI variant is in my spec. So it's really simple to refer to the configuration that the user asked for from the package file. And so that's what enables us to build lots of different versions on demand. You can override stuff in Spack packages. There's a default install method for CMake packages. This particular code happens to not have the most extensive build system, so we made one for it. We just put an install method that copies the executable that it builds into the prefix. And that's fairly easy. There's other stuff you can do in here. You can put patches on things. You can download extra resources. You can declare conflicts with other packages. But it's standard stuff that you would expect in a package. So what's going on when you say Spack install? If you ask for a spec like this, MPI leaks with call path 1.0 plus debug, depends on libzelf at 0811. We call that an abstract spec. You're saying, these are the constraints I care about. I don't care about any of the others, and I don't really want to think about them. And so Spack has this process called concretization, where if a user asks for something like this, so the user puts this on the command line, it says, OK, well, what did they really want? I'm going to go fill in all the blanks. And so it builds a DAG that has everything filled out. And so the reason that we did this is because we found that people who wrote build scripts, they spent a lot of time saying, like, hey, is this installed on the system? Is this installed on the system? What version is it? They would just do all this query code and sort of search for the things that they could build with. And Spack guarantees that all of that stuff is worked out before you even start the install instructions. So essentially, the concretizer takes this abstract spec, turns it into this concrete thing, and it enables the build logic to be much simpler because all you're really doing is translating this into install instructions. And this, I'd say, is one of the key differences between Spack and EasyBuild. If you think about how Spack is structured, it has this notion of a spec, so users can talk about configurations even on the command line. You give that to Spack, and it actually concretizes it and resolves the dependencies dynamically. And then it spits out this configuration, and then the build instructions are applied to that. So if you think about how that relates to easy blocks and easy configs, the easy block is sort of the instructions in the package file that I showed before. And the easy config is basically users writing this kind of graph by hand in the easy config file. So the user has to do the work of concretization in EasyBuild. And so, this is where the solver for the concretization gets all of its inputs, is in these specifications in the package file. So it's sort of a different take on the install process than what EasyBuild does. I already covered sort of the places where Spack's being used. One of the sort of more interesting ones now is it's actually going to be the deployment system on the new Fugaku system in Japan. So that was formerly called PostK. They're going to use it for ARM SVE there. I wanted to show this to sort of emphasize that we do have a very large and growing community. So this is lines of code over time in all of the packages in Spack. And this is lines of code in the core. And so you can see that basically in 2015, we were a Livermore-only project, essentially. I think there were a few other contributors. But after that time, we've just gotten more and more contributions from other organizations to the point where Livermore doesn't really contribute all the packages in Spack. It's mostly other organizations that are putting stuff into it, which is pretty cool. So we actually get a whole lot out of this from the contributors. And even in the core, I mean, we've had a lot of assistance from not just Livermore here, I mean, we're still the main contributor to core, but EPFL, Fermilab, other places, Kitware, have really started contributing to Spack, and we get help even on the core tool. I thought I'd show GitHub stars just for kicks. It's not the greatest metric, but this is the plot. So this is GitHub stars over time for some popular HPC projects. This is Singularity, which is just sort of rocketing to heights of GitHub stardom. This is Spack down here. And then this is Chapel, which is pretty cool. Chapel's getting popular. And then this is Easy Builds down here with OpenHPC. And so they both have strong communities. And I don't know, this is the same data with stars per day because I'm a nerd. So that's the rate of stars in 60-day windows over time. All right. We've done a lot of outreach. We've given tutorials at different places. And actually, if you want to bring Spack to your country, we've recently introduced translations of the Spack docs. So if you want to have your own translation of the Spack docs, there's a whole repo that you can go to do that. And we recently did 1 page of the Japanese documentation. And the idea is that this is what's going to be used to help train Fujitsu employees to use the tool. Spack 0.12 was just released. And the big feature in there was something that we're calling environments. I think that should sound familiar to people who are familiar with Conda or pip or virtualenv. But it's a little different, so I'm going to talk about what that really means. It's also permissively licensed, so this is another difference with Spack and EasyBuild. We're Apache 2 or MIT. You can pick your license. One of them has a patent grant, so contributors basically always have to say, you have the rights to use our patents. And one of them is compatible with GPL2, which is why we did both. So you can pretty much use Spack anywhere. And it's growing. So for environments, this is what the new environments feature looks like in Spack. Who's familiar with systems like Cargo or, I don't know, NPM or package managers like that, where basically it's sort of you have a file in a directory that says what you depend on, and you can install your dependencies that way for say, a project. No? People are not? OK. So in Spack now, people had issues that there weren't really good ways to install lots of packages at once. And so we introduced this feature called environments, where you can write a file like this. So you can say Spack : you can include some configuration if you want to, or you can just inline the configuration in the file. But the big deal is that you can put a list of specs here in the file. And so you can just say, this is an environment with these packages in it. And what this allows you to do is you can put this in a Git repo, or you can put this in a project directory, and you can cd to that directory and just say Spack install. And then Spack will basically go, it will concretize this whole thing. It'll spit out a lock file, which basically lets you reproduce that installation somewhere else in the exact way that Spack said that it was configured there. And then you can build the project from whatever this concretization came out to. It also lets you kind of iterate on the environment so that you can sort of get all the specs the way that you want them when concretized before you install. And it lets you version your configuration. So essentially, if you're a project and you want to say what you depend on so that when people clone your project from GitHub, you can put one of these files in the root of your repo, and then someone can get all of the things they need to build your project by just saying Spack install. That's it. The other kind of cool thing about this is that these double as virtual environments. So in Spack, you can actually say Spack env create and put a name to it. And basically, one of these is maintained within Spack that it manages, and you can activate the environment and have it in your path. And so essentially, you don't need to use modules to use Spack. You can use virtual environments on your laptop. You can use them on the cluster. And Spack will also generate modules for you in the cluster environment, but you don't have to use them. It doesn't rely on them at all. All right, yeah? You use the same syntax that I showed before. So you could write OpenMPI at 1.4 if you wanted to. Yeah, and you could write like OpenMPI with fabric equals whatever if you wanted a particular configuration. You can put basically anything on this line that you could put on the Spack command line. It's the same syntax. So, and what that means is that you can actually use Spack to build containers fairly easily, and you can version this configuration with, say, a Docker file. And so you can have a directory like this where you have a Docker file and a Spack.yaml, and your Docker file just has to look like this. You can say from, and we're providing base images on Docker Hub that come with Spack pre-installed. You can say, here's my working directory, copy the Spack.yaml in there, and run Spack install. And that gets all your packages installed. And you can go and basically, this is your Spack.yaml, and so here's an example. You can say HDF5 at this version. You can say OpenMPI with this option in Nalu if you want all those in the environment. And then you can go and build this with Docker and run it with Singularity or some other tool. Any other questions? I thought I saw a hand. Nope. OK. And so with all of those features, we're moving into a mode where we're starting to think about how we're going to manage the software release for ECP. And so a lot of teams have started using Spack independently, either for their own project or with other sort of related projects to manage group releases. So a lot of the math libraries have been managing a release called XSDK of, I think, Trilinos, MFEM. I think there's like 17 math libraries in there now, PET, Hyper, and a number of others. They all have sort of this periodic common release, and they use a Spack file to basically manage that. And ECP wants to use Spack to manage the delivery of software both to users, to developers, and to facilities across the whole project. And so there's a lot of projects emerging in ECP that are sort of related to this. So I tried to sort of spec them out. Under software technologies, there's a whole software integration area. And that includes the Spack project, which is sort of under this software packaging technologies, and the container stuff. So we work closely together. I'm actually the lead for this project. There's a software development kit project under software integration as well, which is where basically they're managing small releases of related products. And those are all rolled into this sort of larger software release called E4S. And so you can go to e4s.io if you want to learn about this. But this is supposed to be the ECP-wide release. And so Spack is supposed to take all of this stuff and move it over. And basically, there's a collaboration between the hardware integration area and all the supercomputing facilities in the US to set up build pipelines and to set up deployment at the facilities for Spack. And there's a project called ECP Continuous Integration that I'm also involved with, where we're trying to make it so that the facilities can actually have secure continuous integration for users and for the facilities to deploy their own software. And so this is actually a project where we're trying to upstream things to GitLab. We're developing new features for GitLab, and I'll talk about that in a minute. So overall, this is what we expect the release process to for ECP to ultimately look like. So there will be teams in different areas. So there's currently math libraries, visualization. These are probably the two most active ones. I think there's a programming models release area. There's also a tools release area. All of these folks are iterating on sort of their own Spack stack. And so they have their releases of Spack packages. They put new versions in. They make sure that they can get this building across all the different machines. And once they're done, all of this stuff gets rolled into this larger ECP-wide release called E4S. Currently, E4S is it's a container. It's the biggest container you've ever seen. And it contains like 230 things. You can download it. It has modules and everything. It's sort of like a virtual supercomputer environment. I don't really want that to be the final product that ECP produces, because I think that's not really the way to use containers. But it's kind of good for a demo. And it also gives us a sort of reproducible environment to test this stuff with. But ultimately, what we'd like to be able to do is to have the facilities actually running build pipelines and deploying Spack packages locally. And so what we're working on is something like this. We would have GitLab deployed at all the facilities. And they would have their own build pipelines set up there where they're actually generating Spack packages. And this is another difference between Spack and EasyBuild. Spack actually has binary packaging capabilities. So you can take a build in Spack, and we can make a relocatable, or at least mostly relocatable. Some of the packages need some patching. But you can make relocatable binaries out of the Spack packages that are then installable at the facilities. And what we're planning to do then is to actually have a public mirror of all these binaries for basically the Spack distro. And so from these build pipelines locally at these machines, like these are all major supercomputers that people run on, we would have binaries hosted in the cloud so that then Spack users could come along and it would rain Spack packages on them. They would be able to download Spack binaries from the cloud and easily use them on supercomputing machines. So like you could imagine, like right now, if I log into one of the machines at these sites, I'm probably going to be building for a while before anything is running in my environment. But you could imagine with this that someone could get running in a few minutes. And I think that's pretty cool. So like I said, security is a real challenge for this. The facilities do not like automated tasks. Most of them have two-factor login. They require things to sort of run as users. And CI automation requires running arbitrary code. So what do? You're downloading stuff from the internet. You're running it at facilities. That is a security risk. And And all tasks at the HPC centers need to run as some user, like I said. And I think, if you look at most of the CI solutions like GitLab or Jenkins, the runners, the things that actually run the jobs, they all run as the same user. And at least at the NNSA labs, and to a large extent at the Office of Science labs where we have export-controlled stuff, this is sort of anathema to the facilities because they don't want the users to be able to see each other's data. If all the runners that are building software are running as the same user, then we can't really produce a release effectively at the facilities. So the ECP continuous integration project is basically, it's a contract that we put out for bid. We picked a vendor. Onyx Point is actually implementing this. They have a close relationship with GitLab, and they're implementing features so that GitLab will have set UID runners and runners that can support batch systems. And so what that means is that your users can log into a GitLab instance at the facility, and then they will be able to, if they push to their repo, GitLab knows it was them that did it, and it runs the job as them on the machines. And so this is completely integrated with the HPC environment. The batch runners are sort of the same thing, but if you push to the repo, the CI job gets submitted as a Slurm job or an LSF job or a Cobalt job, because our gun runs Cobalt. And there's a library that they've built to actually integrate the GitLab runner with these batch systems. And so we're hoping that we can get a lot of this upstreamed to GitLab. So if you think about this, this is done. The set UID runner that I just described, basically it's one facility, multiple runners. You could put runners on all the clusters, tag them differently, so that users could easily push and run as themselves. Milestone 2 batch runners, this is actually done too. Facilities are starting to run this in production, where it's the same model, but you're submitting to the batch system. The final form of the GitLab runners for DOE is supposed to be multi-site. And so there's going to be an instance of GitLab running on a DOE-wide server. It's actually hosted at an organization called ASTI, which is part of DOE, but it's not at any of the particular labs. But they do GitLab hosting already for some of the sites. They're going to run a DOE-wide server. And the problem here is obviously that this GitLab server has different usernames from all the machines. And so you need some way of federating these accounts and making it so that this thing can run jobs securely on behalf of users. So we'll take the set UID runners that we made and the batch runners that we made already, add an authentication interface at the different facilities that knows about the facility login. So this is your facility two-factor. And basically expose that to GitLab. So GitLab knows about this authentication interface. These runners are deployed here. And if you log in here, you can basically do sort of a social sign-in with the different facilities. You can say, I have an account at Oak Ridge, and it will say, prove it. And you enter your Oak Ridge two-factor credentials. And then GitLab remembers that you can run at Oak Ridge and that your username at Oak Ridge is whatever it is. Same for Argonne, same for Livermore. So you log in, you do some authentications at the facilities, and then you can push here and have your code tested at all the DOE sites. So this is the ultimate goal. It's not the most convenient model yet because you have to do these multiple logins. We'd really like to have federated authentication, but since that doesn't exist in DOE, we went with this model because we don't currently have anything that can work across the sites. But a future project would be to sort of integrate this so that there's actually a single login. And I think people will start asking for this once they see that it's valuable. You could actually run at different sites and test your code in the environment where you want to run. And we're trying to upstream all of this to GitLab. They've asked for some changes to some of the features. I think they will likely add capabilities to GitLab to support these features, but maybe not integrate the entirety of what we're building. But I think that's good, as long as we have hooks and we can distribute our runners in a good way for HPC sites. And the goal is that other sites could use this too. So you could deploy CI for your users at your HPC center so they could actually test on the hardware. I talked about this already, but I mean, essentially this is what Spack looks like right now. You do pull requests, they get tested in Travis. We would like to have both a source and a binary mirror in Amazon that includes, so right now we're actually running builds in the cloud, and we would ultimately add the HPC centers to this so that binary packages could be deployed for basically anyone to use at these different sites. So any questions on that? All right, so on the roadmap for Spack, there's a number of features related to this stuff that we're building to support the ECP deployment process. One of them is something that we call Spack Stacks. This is essentially like environments. We're building on the environment workflow, but we're allowing you to define basically large cross products of specs. And so if you think about most facilities, you have a few compilers, you have a few different MPIs that you support. You don't really want to write over and over in a YAML file this compiler, this MPI, this compiler, this MPI, all the different combinations that you want there, because you have a lot of software. So you can have a file like this where you say, these are my compilers here. I have GCC, Clang, and Intel. This is my list of MPIs. These are my MPI dependencies. And these are the packages that I want to support. And then down here, you can just say, this is my matrix. And we're going to take the cross product of the packages, the compilers, and the MPIs. And that basically takes all of these, multiplies them out, and generates the full list of specs. And this is all installable like an environment. So you can say Spack install this. It'll spit out a lock file with all of that configuration so that you can remember exactly how your stack was built. And you can have a module configuration associated with each stack. And so at Livermore, at least, our goal with this is to support the module schemes that we use at the different NNSA sites. So we collaborate with Los Alamos a lot. They use different module names from Livermore. And when their users get on Livermore machines, they kind of have to tweak their scripts. With this, we think that we could basically provide both module schemes in parallel to each other. You could pick the Livermore one or the LLNL one, and they would share installations. And so because this is basically environments. You can have as many of these as you want with different module configurations. And underneath the environments themselves, the installs are actually shared. So if the configuration is the same, it's going to be the same install regardless of what environment it's in. The other thing we're working on for this binary packaging stuff that I talked about is we really want to be able to include metadata in the Spack spec that allows you to very finely delineate an architecture. So far, Spack has mostly been used to build from source. And so if we mark something x86-64, the meaning of that is different from machine to machine. And so like if you build on a Skylake, you will probably get x86-64 binaries that have Skylake instructions in them that have AVX512. And if you build on a Haswell, you won't. And so if you build on a Skylake and try to run on a Haswell, they're both marked x86-64, so that can be confusing for binary reuse. And if we're going to host this stuff in the cloud, we need much more detailed metadata for this so that we know where each of the binaries can be used. So what we're doing is we're coming up with a model that would actually relate the different short names for architectures like Skylake, Haswell. We're trying to come up with names for the ARM ecosystem, and it's difficult. The different power architectures. And we would have all of those. We would have sort of a library that relates them to each other. So that it would know that, say, Haswell binaries are runnable on Skylake and not the other way around. And it would know that the Skylake instruction set is probably, and I say this like somewhat carefully, like that you would rather run the Skylake binary on the Skylake chip than the Haswell binary, even though it's not necessarily true. You may run slower with AVX512, but assuming that you want to use all the instructions, we would have a way of picking the best architecture from the ones that are available. If you have binary packages out there for Skylake and Haswell and you're running on a Skylake, we'd pick the Skylake one. Or if you only have Haswell and Ivy Bridge and you're running on a Skylake, we'd pick the Haswell one, things like that. This would be integrated with the concretizer so that essentially when you say Spack install something, it would prefer things for which a binary is available, and it would actually try to find the best binary for what you asked for. So it would fit your abstract spec with the best binaries or the best existing installations and try to assemble that DAG in a way that would run the fastest for you. And we have preferences that control how concretization is done already in Spack, so there are configuration files where you can set preferences for that. There would be preferences to allow you to say, whether you really do prefer Skylake to Haswell or things like this. Yeah?
Just kind of a follow-up from a discussion we had yesterday, but when you're thinking about this target architecture stuff, and are you thinking about tagging some packages being more performance sensitive than others? Like in this resolution, maybe it's something that you don't care about and you prefer just to ship out the binary, but it's another package that you really want the optimized version. Are you thinking about having that in your concretizer sort of resolution?
So we're thinking about, the one thing that we're thinking about doing initially, and I guess I'll phase this answer. I think the first thing that we would roll out is basically the metadata support where we do an exact match, right? Just the simplest thing. And so we would just say build the whole thing with the optimized architecture. That's obviously not optimal, right? The second thing that we would probably do is instead of just marking packages explicitly as performance sensitive, we have information in the DAG that tells us, that I don't care about building CMake with AVX512 instructions, right? And I know that because I can look at my DAG and I can say CMake is a build dependency, right? And I know it's not a link dependency. I know it's not used at runtime. And so basically we would take everything that's marked as a pure build dependency and just build that stuff with the easy compiler. And that's helpful not just for this, but because half of that stuff doesn't build with like PGI either.
Not necessarily true, is it?
Sorry?
It's not because it's the build dependency that do not need performance.
Well, you certainly don't care about it at runtime, right?
What if you're statically linking to a library? And it's a build dependency, the library is
The library is not, in Spack's model, the library is not a build dependency there, it's a link dependency.
okay, you have 3 guys.
Yeah, we mark that as a link dependency because we know we're going to link against it. And likewise, if you call an executable from something, it's a run dependency, it's not a build dependency, right? If you call it at runtime. If you call it at build time, it's a build dependency. And it can be both, right? And so we would look at things that are only build dependencies, right? And I have a whole other presentation on the rules that you would have to go through to think about this and rationalize the DAG. But I don't want to get too far into the details there.
What's
yeah.
the status of, you said this could be a separate library that you can leverage in Spack?
There's a PR right now that Greg has written that has most of the metadata for the different architectures and the names and things. And I think what we're sort of trying to decide right now is how we would, whether we want to go more detailed than this, right? Like we have short names right now, but we can get the features, like the specific architecture features from proc CPU info. And so what I'd really like to do is have all the features in the binary so that, under the hood we could match based on features. And, but users could still type Skylake, right? Because the user's not going to enumerate the things that make a Skylake a Skylake. Like there's like 16 of them if you look at what's in, proc CPU info.
But the plan is now to have this inside of Spack.
Yes. So this metadata would get recorded in the spec, right? So in your lock file for the configuration, it would have the exact architecture that the thing was built for. And everything would have an marcher and MCPU argument with it. So we would not have a Spack build that was not built without that argument. And that would also enable you to have like generic binaries, right? So we'll pick a lowest common denominator architecture and say that's generic. And then for some things we may optimize for genericity, and for other things we may optimize for speed, right? So I think we have some freedom there. It's really a policy nightmare, right? Like when you think about how to build the DAG. And so encoding that as constraints for our solver is really the thing that we're working on. So, okay, any other questions on this stuff? All right. So there's a really large open source ecosystem in ECP. We're doing contributions to open source projects like GitLab. And there's this burgeoning sort of software release ecosystem that's happening where essentially ECP is moving towards regular releases for all the software in ECP. This is sort of a hierarchical release process. It's in progress. We're sort of spinning up to have something regular and automated. But all of these things are sort of coming together so that we will have build pipelines running on a regular basis. We will have binary mirrors for Spack packages, and hopefully one day you'll be able to log into a supercomputer and not, I guess, like as Brad said earlier, suffer, right? You'll have a good time when you get on your supercomputer and you could actually install the stuff you want to run and just run it, like on every other computer system, instead of saying like, well, I want to have this software, and then 2 weeks later you're like, I finally have it, right? So this is the goal. I guess we're also contributing to Jupyter Hub, so we have a secure version of Jupyter Hub. I didn't have time to talk about that, but if people are interested in that, talk to me, because we have secure ways that you can deploy Jupyter Hub at your data center if you want to. All right, so questions? Yeah.
One of the issues I've heard people talk about when they use Spack is when they do an update of Spack, just to get pull basically.
Mm-hmm.
Spack doesn't see the installed software anymore in terms of picking up dependencies because some stuff has changed in the hashing.
Sure.
So the hash has changed, so it doesn't pick up on the software anymore, it has to reinstall it.
So the hash for a configuration has not changed, right? We don't change the hash. But when you pull,
the algorithm changes, so you get a different hash.
the algorithm doesn't change. So like the actual, so the way that we hash the records, right, does not change. The hash for the old YAML will stay the same unless we actually change the hash algorithm, which we do really infrequently, right? So what people are complaining about is essentially that when they pull Spack, they get new versions of the package files, right? And currently the concretizer uses the newest version, right? And so when you say Spack, so if you want to use Spack in a facility deployment environment right now, we have releases. You pull down 0.12.1, and you stick with it. And maybe you backport the changes for the packages that you care about if you want to stay stable, but you don't screw with the packages too much, right? If you live on develop and you pull the packages on a regular basis, then what's going to happen is when you say Spack install, it's going to concretize it, and it's going to set the versions in the DAG to the newer versions, and it'll rebuild because it says, well, that's not installed, right? So what we're also working on, and it's actually the same problem that I talked about here with the binaries, is that we want to change the concretizer so it prefers the installed versions if they meet the constraint that the user asked for, right? And that's a little harder because it means that we have to do a full-on backtracking solve as opposed to the heuristic stuff that we do now, because the problem's NP hard, right? And so ultimately, like, you'll be able to say Spack install, and there will be installed packages, and there might be stuff in binary mirrors somewhere, and you can have policies that say which ones you prefer from those places. And it could say prefer things that are already installed on my machine, then prefer things from the mirror, and it would build a DAG with those rules as opposed to what it does now, which is basically just take the latest thing, right? So that's what people are saying. And so people get rebuilds when they maybe shouldn't have to, right? But it's when you update your package files. So if you want a stable installation, pick a release and stick with it, and bring in the package modifications that you want over time. I mean, which is essentially what people do with EasyBuild, right? They pick an EasyBuild release. If you change the configs, you get new versions of the software, and they're going to get rebuilt.
Well, the configs we ship don't change. If you update EasyBuild, you just get more configs.
Right. So if you don't change Spack, it also doesn't change.
But you also don't get support for new software or new versions. So if a package file has to be updated because there's a new release, there's CMake 5,
Sure.
which has, God forbid, changed to using Bazel for building, whatever. The latest Spack release will not know about it. The package file has to be updated, which means that it may affect the hashing.
I guess I'm not seeing how that's different from the easy configs. Like if I add a new config for a new easy build
Because
version.
in the easy configs, all the versions are fixed.
Are fixed. Yeah, well, the Spack installs, all the versions are fixed.
Eventually, yes, but you will still run into the hashing problem, I think. If you have to update the package file to tell it how to deal with the new CMake, that may affect the hash, which means you may have to specify more things to convince the concretizer to.
If you want to fix the version of CMake in the package file, you can put preferred equals true next to the version that you want it to stay at, even if you keep updating the versions.
Okay, so that could be a workaround to
Yeah, you
avoid
can do
the
that.
hashing problem, yet still have support for installing them.
And you can also fix your versions in the packages.yaml, like there's a preferences for concretization. If you want to fix the version of CMake, you can just say packages : CMake : versions, whatever you care about.
That's a general configuration?
Yeah, it's a Spack-wide configuration. You can do it within an environment. So like for one of these like stacks, you can say these are the versions I prefer, right? And so you can actually just build a release that way. And I guess so right now we don't have releases in quite the same way that EasyBuild does because we don't have this CI infrastructure, right? And so what we'd likely do is ship the latest release that was certified, right, via this process and say prefer those versions, right? And so that could be another input, right? You can prefer what's installed, then you could prefer whatever was in the latest release, then you could prefer to fetch something, and only then would you actually go and build something, and so on. Yep.
What do you do the sanity check in some campaigns? So you might get some combination that nobody has ever done before.
Sure.
So what does Spack do the sanity check the end result?
So you rely on the packagers for that, right? Like in the package, you can say I depend on this version range, and you can say I conflict with this other version range. So if you know that something doesn't build with something else, right, then you can mark it as a conflict. But I mean, in general, like we don't want to limit what people can build with Spack. Like, and so if we don't know that something's not allowed and you want to try it, you can write that down. We're not going to sit there and tell you like, oh, no one's ever tried this before, right? Like the whole goal of HPC is experimentation and building new things. And so to some extent, like, that's on you. If you want to take on a new build that no one's ever done before, then fine.
But do you have a mechanism? I just don't know. I haven't used it honestly.
Yeah.
If you have a mechanism for people to add certain sanity checks, like commands or executions or something that they can say, like,
Yeah.
run this and see if it works.
So you can
It's the same installation.
you can add sanity checks to the packages that get run after install. And so you can check for like the existence of files and things like that. But we don't currently have like a testing infrastructure for this, like or ways to run like the test suite for a package after you install a package. That's not in there.
And so then in the ECP environment, then how would you check for performance then? Right? So say you have the mechanism now to put the software in place.
Right.
But what about the performance of that software?
We would have to test it. And I mean, like there's systems like Reframe that we could run, right? And I mean, I think it would be wiser for us to integrate with those than to necessarily implement a whole testing framework here. And I mean, at Livermore, we have something called SWL, which builds on this thing called Pavilion from Sandia. And we test our clusters for acceptance that way. Yep.
So somewhat related to that, I disagree with your point where you say HPC is for experimentation, and if you choose to build with the latest and greatest, want to play around with that, you should. I agree with that part.
Okay.
But currently that's the default model in Spack. If you do Spack install OpenFOAM, chances are pretty high that you're going to get a combination of things that nobody has ever used before, which means you'll have to be very careful with testing it before you put it into production and give it to users, because maybe there's a netcdf update and Spack knows about it, it installs it as a dependency for OpenFOAM, but OpenFOAM doesn't like it.
True.
And you really only know when you start using OpenFOAM. How do you know how well you have to test it before it fails?
I mean,
and this differs from EasyBuild in the sense that because we fix all the versions, I mean, we don't test it
right.
very extensively.
You test it on your cluster.
But at least we know that multiple people are using the same setup. And if a problem pops up, it will be reported to EasyBuild and say,
So I guess I still don't understand that concern, because like if you clone Spack 0.12.1, you're using the same configurations as everyone else who's using Spack 0.12.1. And you keep it there.
You get the same default configurations.
Yes.
But as soon as you start giving more stuff to the concrete guys, you're building something that probably nobody else has built.
If I upgrade to a new version of Spack, yeah, then I get.
No, even with the fixed version of Spack.
No.
I can do Spack install OpenFOAM netcdf 4.3, right?
Yeah.
If you do this because for some reason you think you need netcdf 4.3, you would still have to be very careful about testing it because you don't really know whether somebody else has tried that before.
Sure, but I asked for it. Like, I don't know. So like if you use EasyBuild, you can't even do that, right? Like you clone that version, you can't install some other version because you don't have an easy config for it, right? So like, I don't know what the difference is. Like, yes, we give you more rope to hang yourself with, but we also give you more capabilities. Yeah. So like, I don't think that's a problem.
It's not necessarily a problem, there's a certain tension there between flexibility and...
Well, there is, but that's what this infrastructure is for, right? So we're trying to have a set of certified and default versions for Spack that would actually be tested. But like, right now, I'm not providing a guarantee, right? Because we don't have like an overnight test infrastructure, and like even if we did, it would be on like one cluster.
EasyBuild doesn't give you strong guarantees either. But
right,
yeah.
So, which is what is confusing to me, because like if I pick 0.12, I get the 0.12 versions. If someone has Spack 0.12 installed 2 places and they say Spack install OpenFOAM, they'll get the same OpenFOAM.
Yeah.
Right? Yeah. Like there's no, confusion there.
So what you're going to do when you have CI infrastructure, what kind of configurations are you going to test? You're going to test Spack install OpenFOAM, make sure that works, Spack install all the defaults.
So that's it. So this is the kind of cool thing, right? We can choose slices of the space. Yeah. And so what we will likely do is make a set of Spack stacks that are, or a central Spack stack that's the default one, right? That has multiple cross sections of the space. We'll pick compilers we care about, MPIs we care about. We may multiply them together. We may just pick combinations. But essentially with the syntax that I showed, you can pick arbitrary combinations. You can say, these are the configurations I'm testing. Yeah. And another kind of interesting thing about that is that like, if we get there, right? And we have all these testing things going on. What I can do when someone says Spack install OpenFOAM with a custom version, right, is try to keep the configuration as close to a tested version as I can, right? I can make the optimizer, the concretizer actually prefer configuration options that are most like the tested version and only change the minimal set of things. And so like, you could think of it as like snapping to something safe, right? And you pull it a little far away from that in the configuration space if you want to try something new, but you stay safe for everything else.